In section 3.6, we look at rational functions. The definition of a rational function is that it is a function that is the quotient of two polynomials. So here we have r of x is equal to p of x, which is a polynomial, divided by h of x, which is a polynomial. And the stipulation is that h of x cannot be a constant polynomial, meaning that the denominator has to have a variable. So in the first example, let's consider the rational function f of x equals 1 over x minus 1. We want to look at the domain of a rational function, a table of values, a graph of the rational function, and then we'll make some comments about the behavior of the graph. So first of all, what is the domain of this function? Well, we know that when we have a fraction, the denominator of the fraction cannot be equal to 0. So if we set the denominator equal to 0, we find out that x is equal to 1 makes the denominator 0. And this means that x cannot be equal to 1. So the domain is all values of x except for 1. And in interval notation, that looks like this. In the second part, they ask us to make a table of values of x and f of x, and they want us to include values of x that are near 1. So, in other words, they want to know what happens near the value that is restricted from the domain. And they also want us to plug in larger values of x. So rather than me doing this by hand, I'm going to go ahead and import the table. And so here we have some tables of values. And if we zoom in a little bit on that, you can see that at x equals 1, the function is undefined. And then we have some values right around x equals 1. So a little bit to the left of 1 is the value 0.9. A little bit to the right of 1 is the value 1.1. And when you plug in those values, you get negative 10 and positive 10 respectively. And in case you're wondering, what's going on here, I will just remind you of what you're doing when you're plugging in a function value. So f of 0.9 means to plug 0.9 into your function. So we're literally replacing x with 0.9. And this gives us 1 divided by 0.9 take away 1 is negative 0.1. And you can do this on a calculator, or you can also do this by hand by just changing negative 0.1 to negative 1/10. And 1 divided by negative 1/10 is the same as 1 times negative 10 over 1, which is negative 10. So that's how they get the function value there. And all of the rest of these values are found by plugging these numbers into the function. So I won't show all the work for that, but I will say that you should definitely be able to do that with a calculator. Now for the third part, they want us to graph the function f by hand. So let's bring in a graph and take a look at what it looks like. So to do this graph, we're going to go ahead and plot some of the points that we have in our table. So you can see that when x equals 0, we get negative 1, as this point here. At 0.5, which is x equals 0.5, which is 1/2, f of x equals negative 2. At 0.9, which is just a little bit to the left of 1, so 0.9 on the x-axis is right about there, and the y value there is negative 10. So we'll drop down and put in that y value there. Oops, sorry about that. We got on the wrong page there. All right, so that's where that value is. And then we also have the value negative 10. So when x is negative 10, the y value is negative 0.09. So x equals negative 10 is here. Negative 0.09 is very close to 0. So that's going to be right about there. And then we'll go ahead and graph some of the positive values as well. So on the positive side of things, when x is 1.1, y is 10. 1.1 is here, and y equals 10 is up there. And then we have 1.5, x equals 1.5, and then y equals 2. That's right about here. X equals 2, y equals 1. And then we have x equals 10, y equals 0.1111. That's this point right about here. So if you sketch what this curve looks like, it is doing something like this. And on the other side, looks very similar. And you'll notice that we get this very peculiar behavior right around x equals 1, because of course at x equals 1 it's undefined. What's happening as the function, as the x values are getting closer to 1 on the right side, is the function values are getting larger and larger. So what's happening there is they're actually going to infinity, and as x gets closer to 1 on the left-hand side, you'll see that the function values are going to negative infinity. So this behavior that you see here is called asymptotic behavior. And we call it asymptotic behavior because right there at x equals 1, we have what is called a vertical asymptote. So I will draw a vertical line at x equals 1. And this is what that line looks like. And again, that's called a vertical asymptote. And so we typically do this when we have a restricted value from the domain. Typically, I say, because we don't always do that. And then you'll also notice that as the values of x are getting larger, the values of y are coming down and getting closer to the x-axis, but you'll notice that it never touches the x-axis. And we know this because we can see that as we plug in larger values of x, the values of y are getting smaller, but they're always positive. And the same thing happens on the left-hand side. As we plug in larger and larger negative values for x, you will see that these numbers are getting closer and closer to 0, but they are always negative. So that's why we're always slightly below the x-axis here. So what is happening here is we have asymptotic behavior in this direction as well. And so the line that I'm drawing here is the line y equals 0, and this is a horizontal asymptote. Now we will talk more about horizontal asymptotes later in the section because they are a little bit trickier in terms of determining, what they are. But this is the basic graph of the function. Now, part D says comment on the behavior of the graph. I pretty much did that already. So the defining attributes of this graph is that we have this kind of bizarre behavior around these asymptotes. Okay, next I want to talk about something that this book calls the large-small principle. And it's actually really useful to just have this concept understood, especially as you move toward calculus. We talk about this a lot. But the idea is this. When we say large, we're talking about a large number. And when we say small, we're talking about a small number. Now, it doesn't really matter if the number is positive or negative. So in other words, if I had negative 1 million, you don't think of that as a small number. That's a very large number that happens to be negative, right? So when we say large, we're talking about large positive or large negative. And when we say small, we're talking about numbers that are close to 0. So numbers like 0.01 would be a small number. Numbers like negative 0.01, that would also be a small number, okay? Numbers like 1,000 or negative 1,000, these would be considered large numbers. And the principle goes like this. When you take the number 1 and you divide it by a large number, you get a small number. And if you take the number 1 and you divide it by a small number, you get a large number. And you can play around on your calculator to verify this. Just take 1 divided by 1,000,000 and see what you get. And then take 1 and divide it by a small decimal and see what you get. Okay? So this is a very useful concept to understand and be able to quote when needed. Okay, so next we talk about vertical asymptotes, which we discussed a little bit on the previous page. To find the vertical asymptote of a rational function, first make sure that your numerator and denominator have no common factors. If that is the case, then the vertical asymptotes occur at values of x where the denominator is equal to 0. And at these values of x, the function will approach positive or negative infinity. So I talked about this on the previous page, right? So we have a vertical asymptote here at x equals 1. And as you approach x equals 1 from either the right side or from the left side, you can see that the function is either going to negative infinity or going to positive infinity. So that is what they mean when they talk about vertical asymptotes here, and the fact that they approach positive or negative infinity. So in the second example here, we want to identify the vertical asymptotes of these functions. And we can do this without graphing. So for example, in the first one here, we have f of x equals 2x over x plus 1. Notice that there are no common factors between the numerator and denominator. So it satisfies the condition that it is in simplified form. To get the vertical asymptote, simply take the denominator and set it equal to 0 and solve that equation. So the vertical asymptote of the first function is going to be x equals negative 1. For the second function, we have f of x equals x plus 2 over x squared minus 1. Once again, to find the vertical asymptotes, simply take the denominator and set it equal to 0. And we can solve this a couple of different ways. I think the easiest way to solve this would just be to add 1 to both sides and then take the square root of both sides. Now don't forget, when you take the square root of x squared, technically that is absolute value of x. And when that's equal to 1, that means that x itself can be positive or negative 1. So the vertical asymptotes are x equals 1 or x equals negative 1. And I should just mention that you can also find the vertical asymptotes here by factoring the original function. So in the numerator, we have x plus 2. In the denominator, we have x squared minus 1, and we know that this is the difference of two squares. So we can factor that into x minus 1 times x plus 1. And from there, you can simply set each of these factors equal to 0. And when you do that and you solve the resulting equations there, you see that you get the same answers that we got over here. So that's just another way to approach it. For the last one, we have the function f of x is equal to x squared minus 3 divided by 2x plus 1. Once again, to find the vertical asymptotes, we set the denominator equal to 0, and we solve the resulting equation, and for this one we get x equals negative 1/2. And these are all vertical asymptotes because if you graph lines where you have x equals a number, those are always vertical lines. Now let's discuss horizontal asymptotes. This is a little bit trickier. And I don't want you to be intimidated by what you see here, because this can be a little bit intimidating. But we have r of x as a rational function, p of x divided by q of x. Notice that p of x has a degree of n, while q of x has a degree of m. And we're going to assume that P of X and Q of X have no common factors. If you have common factors between the numerator and denominator, then that requires an additional step that we'll talk about later. Okay, we have three situations here. If n is less than m, meaning the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is y equals 0. And they say that r of x approaches 0 for large values of absolute value of x. So that just means as x gets bigger, the y values are getting smaller. So if n is less than m, y equals 0 is the horizontal asymptote. If the degree of the numerator is equal to the degree of the denominator, then the rational function approaches the non-zero constant an over bm for large values of absolute value of x. And the line y equals an over bm is the horizontal asymptote. Now, that sounds a little confusing, but it actually isn't terribly confusing. All they're doing is they're saying that when this degree here and this degree here are the same, then the horizontal asymptote is going to be y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. And finally, if the degree of the numerator is larger than the degree of the denominator, then the function has no horizontal asymptote. And we have some examples down below here that should help clarify what we said above there. So in the first example, we have f of x is equal to x plus 2 divided by x squared minus 1. Notice that x plus 2 is x to the first power plus 2, and then we're dividing that by x to the second power. So in this one, the degree of the denominator is larger than the degree of the numerator. And so the horizontal asymptote here is going to be y equals 0. In the second function, we have f of x is equal to 2x, which is 2x to the 1, divided by x plus 1, which is x to the 1 plus 1. So here you should see that the degree of the numerator and the degree of the denominator are equal. And so to get the horizontal asymptote in this case, what you do is you identify the leading coefficient of each of these polynomials. Well, the leading coefficient of the numerator is 2, and the leading coefficient of the denominator is 1. And so the horizontal asymptote is going to be 2 divided by 1, which is 2. So y equals 2 is the horizontal asymptote. And for the third function, we have f of x equals x squared minus 3 divided by 2x plus 1. Again, keep in mind that 2x is the same as 2x to the 1. And so here we have the degree of the numerator is larger than the degree of the denominator. And in this case, there is no horizontal asymptote. Okay? And all of these were summarized up above here. All right? But this is the practical application of that. Now let's talk about sketching the graph of a rational function. And I will just start by saying, in this day and age, sketching graphs can seem a little bit archaic because we have so much technology these days and so many really great graphing calculators and programs that you can easily find online that some people kind of wonder, what's the point of even discussing graphing of rational functions? And I will say that it's the behavior of the function around the asymptotes which is really important when you're graphing rational functions. So yes, you can always get a graph very easily by using an online graphing calculator, but we still want to have a basic understanding of the behavior of these rational functions. So here are the steps for graphing a rational function. First of all, you want to find the vertical asymptotes and indicate them on the graph. Second, find the horizontal asymptotes and indicate them also on the graph, and we just talked about how to do that in the previous two examples. Then you should find all X and Y intercepts and put these points on the graph. And so these are the points where the graph will cross the x-axis and the y-axis. And then you use that information to sketch a partial graph. So we're going to just connect those points and think about asymptotic behavior and try to get a rough sketch of the curve. Also, you can determine whether the function has symmetries. Rational functions don't always have symmetries, but sometimes they do, and if you recognize it, it can make the graph a little bit easier. And then if needed, you can always plot some additional points to help complete your graph. So let's go ahead and take a look at a full example here. So in this problem, we want to sketch the graph of the function f of x equals 2x over x plus 1. Now, we've already found the vertical and horizontal asymptotes on the previous pages, but let's go ahead and summarize them again here. So for the vertical asymptote, we set the denominator equal to 0, and we find that x equals -1. For the horizontal asymptote, we identify the degree of the numerator and the degree of the denominator, and once we notice that they have the same degree, the horizontal asymptote is going to be y equals the leading coefficient of the numerator, which is 2, divided by the leading coefficient of the denominator, which is 1, and this gives us y equals 2 for the horizontal asymptote. So we can go ahead and start sketching a graph and put those lines on that graph. So the vertical asymptote is x equals -1. That will be a vertical line which passes through the x-axis at -1. And the horizontal asymptote is y equals 2. And that is a horizontal line that crosses the y-axis at 2. And the reason you always graph these first is because, once again, we know that as the values of x get close to the vertical asymptote, we know the function is either going to go to infinity or it's going to go to negative infinity on both sides, right? It's going to be one or the other. And that really helps us when we're trying to find the basic features of the graph. For the horizontal asymptotes, that tells you more about the end behavior of the graph. In other words, as x gets large, we know that the values of the function are going to be getting closer to the horizontal asymptotes. And as x gets large in the negative direction, same thing is going to happen. So the next thing we want to do is go ahead and find the x and y intercepts. So let's do the x-intercepts first. To find the x-intercept, you need to set the function equal to 0. The function is 2x divided by x plus 1. And if we set that equal to 0, we then solve for x. And the only way a fraction can equal 0 is if the numerator of the fraction is equal to 0. So 2x over x plus 1 equals 0 means that 2x has to be 0. And so we get x equals 0. So the x-intercept is the point 0, 0. So I'll go ahead and put that point on the graph. And I want you to notice that this is also the y-intercept, right? Because 0, 0 is special. It crosses both the x and the y-axis. So we don't really need to find the y-intercept in this case because we already found it when we found the x-intercept. But I'll just remind you that to find the y-intercept, what you do is you let the number x equals 0. And so we do f of 0. And in this case, that means plugging 0 into this function. And so that is 2 times 0 divided by 0 plus 1, which is 0 divided by 1, which is 0. And again, this is the point 0, 0, as I mentioned already. So finding the x and the y-intercept is a little bit unfortunate because it only gives us one additional point on the graph. This is not enough information to sketch a graph, right? Like, we need more points to be able to sketch a decent graph. So what I'm going to do off to the side here is I'm going to make a little table of values for the function. And I'm just going to plug in some additional x values so that we can get a decent sketch of the graph. So the question is, what x values do you want to choose here? Well, we could choose any x values that we like, but what I like to do is look at the graph that I have here, and I should probably pick some points that are on my graph. So maybe I'll plug in x equals 5, for example, and maybe I'll plug in x equals -5. And then we should also plug in some numbers getting close to x equals -1. So let's plug in +5, let's plug in +1, and let's plug in -1/2. Okay, so those are all numbers that are over here. I don't need to plug in 0 because I already have that. And then on the negative side, let's plug in -5. And how about if we plug in -2 and -1.5 or -1.5. And let's see what we get. So to do this, you can use a calculator if you like, but again, you can do this by hand. So for example, f of 5 is going to be 2 times 5 divided by 5 plus 1. And this is 10 divided by 6. 10 divided by 6 is the same as 5 divided by 3, which is 1 2/3. Or if you did this on a calculator, you would get 1.667. And so when x equals 5, which is here, y equals 1 2/3, which is right about there. And you don't have to have absolute precision when you do these. All right. So I'll go ahead and fill in as a decimal here. When you plug in 1, you're going to get 1 because 2 times 1 is 2, and 1 plus 1 is 2, and 2 divided by 2 is 1. So the point 1, 1 is on the graph. And when you plug in -1/2, that's going to give us 2 times -1/2 divided by -1/2 plus 1, and this is -1 divided by 1/2, and that is -2. So when x equals -1/2, y equals -2, which is right there on the graph. And this is very valuable because now we know what this function is doing. We know that as we get close to -1 on the right-hand side, the function is approaching -infinity. That's pretty clear. And as we plug in larger and larger values of x over here, it's approaching this horizontal asymptote, but from below. And so the sketch of this graph is going to look something like this. And again, we don't have to have a perfect graph here, just one that accurately describes the behavior. Now we do the same thing for the negative values that I have over here. Let's go ahead and plug those into the function, and I will skip the work here and just write down those answers. So here are those y values. And we'll go ahead and plot those on the graph. So we have the point -5 for x and 2.5 for y, which is right about there. -2 for x gives us +4 for y. And -1.5 for x gives us y equals 6, which is right about here. And again, if I just sketch the basic behavior of this graph, we can see that as we get close to -1 on the left side, the function seems to be going to infinity. And as you plug in larger and larger negative values of x, the function is approaching this horizontal asymptote. And so here is a sketch of the graph of that function. Let's go ahead and do another one. So here we want to sketch the graph of f of x equals x plus 2 over x squared minus 1. For the vertical asymptote, we set x squared minus 1 equal to 0. And we actually solved this earlier. So you can solve this by taking a square root of both sides here, and we get x equals plus or minus 1. That means that x equals 1 is a vertical asymptote, and x equals -1 is a vertical asymptote. For the horizontal asymptote, notice that the degree in the numerator is 1. The degree in the denominator is 2, and when the degree in the denominator is larger, then the horizontal asymptote is y equals 0. Let's also find the x-intercepts and y-intercepts while we're at it. So to get the x-intercept, we set the function equal to 0, which means x plus 2 over x squared minus 1 equals 0. And then remember, the only way a fraction can equal 0 is if the numerator of the fraction is 0. And this means that x equals negative 2. So the x-intercept is the point negative 2, 0. To find the y-intercept, we plug 0 into the function. So when you plug in the number 0, you get 0 plus 2 over 0 squared minus 1. This is 2 divided by negative 1, which is negative 2. And so that gives us the point 0, negative 2. So now that we have our horizontal and vertical asymptotes, our x and y intercepts, we can now start to sketch the graph. So to do this, we'll go ahead and put down our vertical asymptotes first. Those are x equals negative 1 and x equals positive 1. So that is this vertical line here and this vertical line here. And then for our horizontal asymptote, we had y equals 0. Y equals 0 is the x-axis, and so that would just be this line here. And we could label these. This is y equals 0, this is x equals negative 1, and x equals positive 1. And then for the x-intercept, we have the point negative 2, 0, which is this point right here. And for the y-intercept, we have the point 0, negative 2. And this brings up a perfect opportunity to talk about something that can happen when you're graphing these functions. And that something is that you can actually get a point that touches a horizontal asymptote. But the function will never touch the vertical asymptotes. Okay, so that's why, if you're wondering, that's why I always do my vertical asymptotes in red. These are restricted. The function can never have a point on a vertical asymptote. However, horizontals can be crossed, okay? Typically, horizontals are not crossed, but it can happen, and you can see that it is happening here. All right, so the next thing I want to do is get some additional points because we do not have enough points to get an accurate graph of this function. So let's make a table of values, x and f of x. And remember that your function was x plus 2 divided by x squared minus 1. And I need to plug in some numbers over here. I definitely need to plug in some numbers in between negative 1 and positive 1. And then I need to plug in enough numbers over here. So I'm going to pick those x values and write all those down. So here are the values that I've chosen to plug in. And you'll notice this is quite a bit of work. We have a lot of work to do to plug all of these numbers into this function. Now, I'm not going to show the work for all of these, but I'll show you the work for maybe 1 or 2 points just to make sure that we understand what we're doing here. So, for example, when x equals negative 5, f of negative 5 will be negative 5 plus 2 divided by negative 5 squared minus 1. And this is negative 3 divided by 24. And that can be simplified to negative 1/8. And negative 1/8 is negative 0.125. Okay, so you can always get a calculator approximation that works well for this. And let's go ahead and plug in another value. Let's plug in 1.5. So f of 1.5 would be 1.5 plus 2 divided by 1.5 squared minus 1. 1.5 plus 2 is 3.5. And then in the bottom we have 1.5 squared, which is 2.25, and then minus 1. And so we end up getting 3.5 divided by 1.25, and then you can use a calculator to get the decimal approximation for this. And that is 2.8. So now I'll go ahead and fill in the rest of the function values without showing the work so we can get on with the graph here. All right, and here are those values, and this took me a substantial amount of time to get all these, and so, you might spend a good 5 or 10 minutes plugging these in, even with a calculator. Now let's start graphing these points, and you'll notice that I did add an additional point down here, and I'll talk about that in just a second, but let's start with the positive values here. So at x equals positive 5, we have y equals 0.29. So at positive 5, y is 0.29, which is less than 1, right about there. And then at x equals 2, we have y equals 1.33, which is right about there. X equals 1.5, we have 2.8, so that point is right about there. So we get a pretty good idea of what's happening on this side of the graph, right? So we know that we have this asymptotic behavior here, and we know that as this comes down, it is going to get closer and closer to that line without touching. In the middle section of the graph, when you plug in negative 0.5, you get negative 2, which is kind of interesting because at negative 0.5, negative 2 is right about here. And then at positive 0.5, we get negative 3.33, which is this point here. And so this is kind of strange. We don't really know what's happening there. So what you could do here is you could plug in another value in between negative 0.5 and 0. And that value would be maybe a value like negative 0.25. So let me go ahead and add that to my table just to see what we get there. And for that, we get negative 1.87. Okay, so at negative 0.25, which is this value here, we get negative 1.87, which is a little bit above negative 2 there. So we get that point. And then you might also want to plug in another point a little bit closer to negative 1 if you really want to understand what's happening there. So I might plug in negative 0.75. And if we plug that into our calculator, we get negative 2.86. And so at negative 0.75, which is right about there, we get negative 2.86, which is down here. Okay, so kind of strange, but it seems like what is happening in the middle here is our function is coming up like this, and then it turns around and it goes back down, and we know it's going to be approaching those vertical lines from either side here, right? Okay, and then finally, for the negative values that you see over here, let's graph those. So at negative 1.5, right, we have 0.4. So negative 1.5, 0.4 is right about there. And then at negative 3, we have negative 0.125. So that's a little bit below the x-axis. At negative 5, we also have negative 0.125. So that's also a little bit strange. So that's why I plugged in negative 4. When you get negative 4, you get like negative 0.13, which is just ever so slightly lower. So what's happening here is the function is coming through the x-axis, gets a little bit low here, and then begins to slowly come back up and approach that horizontal asymptote. That is what is happening there. And then we can kind of assume that we know what's happening here is this function is likely going up like this. You could plug in another value close to negative 1 here to make sure that that's happening. I will tell you, though, that is what's happening. And so this graph is going to look something like that. So what you should get from all this is that graphing rational functions is extremely tedious, right? I mean, this is not a simple thing to do. Let me go ahead and do it on an actual graphing calculator, and I will bring in that picture so we can compare what we got to what it would look like on a computer. So here is a side-by-side comparison of the graph that we created by hand and a graph from a graphing calculator. And you should be able to see that we did a pretty good job here. If you graph the vertical asymptotes here and here, you can see the correlation between the two graphs a little bit better. And here is the horizontal asymptote. And you can see that we've captured this behavior quite well, right? You can see this section of the graph is here. This section of the graph is right here. We did that section really well. And lastly, this part of the graph is reflected over here. So you can actually get really good graphs graphing by hand. It just takes a lot of time to do it. And you should spend the time practicing for sure. So next we're going to talk about rational functions with slant asymptotes. Now a slant asymptote is an asymptote that is neither horizontal nor vertical. It's a slanted line. And the function will get close to that slanted line as the values of x get larger. So when does this occur? Well, it occurs when the degree of the numerator is exactly 1 larger than the degree of the denominator. When this happens, you will always have a slant asymptote. Now, here's what it means in long division. So we'll talk about this when we do an actual example. And then what happens when you have a slant asymptote is that the rational function will get closer and closer to that line as x gets larger in the positive direction or as x gets larger in the negative direction. So let's go ahead and take a look at this example here. So for this function, I want you to notice that the degree of the numerator is 2 and the degree of the denominator is 1. So the degree here is exactly 1 larger than the degree here. Now, we still have a vertical asymptote, so let's talk about the vertical asymptote for this graph. That's going to be when the denominator is equal to 0, and if you solve this equation, you will get x equals -1/2. For the horizontal asymptote, there is none, because when the degree of the numerator is larger than the denominator, you don't have a horizontal asymptote. However, because the degree is exactly 1 larger, we will have a slant asymptote for this graph. So to find that, what you need to do is use long division to divide the denominator into the numerator. And so we'll go through this long division process. 2x divides into 6x squared, exactly 3x times. 3x times 2x is 6x squared. 3x times 1 is 3x. And then we have to subtract. So this gives us -4x minus 1. And then we take -4x and divide it by 2x. And that gives us -2. So we get -2 here, and then we multiply -2 times 2x, which is -4x. And -2 times 1 is -2. And then we subtract and combine like terms here, and we get 1. So what we know is that the function 6x squared minus x minus 1 over 2x plus 1 is equal to, so now we take the quotient, which is 3x minus 2, plus the remainder, which is 1, over the original divisor, which is 2x plus 1. And once you've completed that long division, this portion is your slant asymptote. So our slant asymptote, which I will abbreviate SA, is the line y equals 3x minus 2. So now what does that mean in terms of the graph of this function? All right, so let me erase some of this so we have room to bring in a graph. So first of all, let's go ahead and graph our vertical asymptote, which occurs at x equals -1/2, which is this line right here. So that is a vertical line crossing the x-axis at -1/2. Okay, so that's the same. And now the slant asymptote is this line y equals 3x minus 2. Well, this is a line that has a slope equal to 3 and a y-intercept equal to -2. So it's going to cross the y-axis at -2, and a slope of 3 means you go up 3 over 1. Do that a few times, and then we can graph that line, and I will make it a dotted line because it is an asymptote. You always graph your asymptotes with dotted lines so that you can tell them apart from the function that you're graphing. And what it means is that now as the values of x get larger, the function values are going to be getting closer to this line. Okay, so that is what happens. Let's bring in some points, and for this I will do this off camera. So I'm going to plug in some values of x so that we can get some y values so that we can try to see what's happening here. All right, so here are the values that you get. And you'll notice that I had to change my graph a little bit because the values that I got over here did not fit on the graph that I had on there. So I had to bring in a slightly different scaling. So notice that every mark on this graph is 2 units now, okay? So when x is -3, y is -11.2, so that will be x equals -3 is right here, and then -11.2 is right about there. And then when x is -2, which is right here, y is -8.3, which is just a little bit below that point. And at -1, which is right here, y is -6, which is right here. And it's very difficult to see what is happening there, but what's going to end up happening is this graph is going to turn around and go down forever. And to show that, what I can do is I can plug in an additional point here where it's a little bit closer to the vertical asymptote of -1/2. So -1/2 is -0.5. What if I plugged in -0.51? Let's see what we get for that one. And if you plug that into your calculator, you get -53.53. So what I'm saying is, as you get really, really close to -1/2, but still on the left-hand side of that, the function value is becoming a very large negative number. And so what that means in terms of the graph is that it is coming in like this, and at some point it turns around and goes down forever. Now, what I really want to focus on is as you get close to, as you plug in larger and larger negative values, the graph here is going to get closer and closer to this slant asymptote. So it's going to look kind of like this. Okay, now let's graph the numbers on the other side. So for this, we have x equals 0, y equals -1. So 0, -1 is right here. And then we have x equals 1, y equals 1.33. It's right about there. X equals 2, y equals 4.2. And x equals 3, y equals 7.4. And so you can definitely see that this is happening here. And if you plug in numbers close to -1/2, you will notice that this is happening over here. So that's a kind of a strange graph, right? Because you have this really kind of strange behavior in here, and it's very, very tight in terms of the scaling of the graph. So once again, I'm going to bring in a comparison graph from a graphing calculator so that we can see it a little bit better. All right, so here is the graph that we made on the left, which again is kind of hard to see here. You could zoom in a little bit, see it a little better. But here's the graph from a graphing calculator. And you'll also notice that on this graph, I changed the scaling of the x-axis a little bit to spread out the graph a little more horizontally. Now you can see the vertical asymptote here at x equals -1/2. And you can also see the slant asymptote at y equals 3x minus 2. And you get a much better idea of what's happening here. So as we plug in larger values of x, you can see the function is getting closer to that slant asymptote. Very, very close. And of course, for the vertical asymptote, as you plug in values of x close to -1/2, you will see that you get that infinite behavior. And the same thing happens on the negative side. As we plug in larger negative values, you can see the graph is getting closer to that slant asymptote. And of course, as we approach the vertical asymptote, the values are getting closer to it. So that is a little better picture than the one that we made, but I am still pretty happy with the graph that we made here. It was reasonably good. Now let's take a look at a rational function that has common factors in the numerator and the denominator. So here is an example. We have r of x is equal to x minus 1 over, and then x squared minus 3x plus 2, that can be factored. It can be factored into x minus 1 times x minus 2. And you could verify that if you want. And I want you to notice that there is a common factor of x minus 1 in the numerator and the denominator. So those can be canceled out. And this becomes 1 over x minus 2. So essentially, the rational function is just 1 over x minus 2. However, there is one special thing that we need to take into consideration. So we know that no matter what, x cannot be equal to 2 because 2 take away 2 would be 0. But even though it appears to no longer be an issue, if you go back to the original function, you can see that x cannot be equal to 1 here. Because if you plug in 1, you get 1 minus 1 is 0. And that would have given you 0 on the top and 0 on the bottom, which is still undefined. So even though it looks like that is no longer a problem because the x minus 1 factor is gone, we still have to take into consideration that original restriction. Okay, so now the difference is this. When you're graphing this, for your vertical asymptotes, you only concern yourself with the factors that are still present. So the vertical asymptote is going to be when x minus 2 equals 0, which means when x equals 2. X equals -1 is not a vertical asymptote. X equals +1 is not a vertical asymptote. X equals 1 is what we call a hole in the graph. All right, so we'll keep that in mind when we go ahead and sketch our graph. Just for reference here, the horizontal asymptote for this is y equals 0 because the degree of the denominator is larger than the degree of the numerator. And so now we should be able to sketch a reasonable graph. So here is a graph with our vertical and horizontal asymptotes. And down below here, I picked some values of x to plug in. And these values are somewhat near the asymptote. And I went ahead and computed those y values. You might want to double check these. And you'll notice that I actually plugged 1 into the function, right? Now remember, we already said in the beginning that x can't be 1. But because we don't have a vertical asymptote there, and because when you simplify it, it's no longer an issue, I can still plug 1 into this, which gives us x equals 1, y equals -1. But then when I go to graph that over here, I need to make sure that I represent that with a hole because we know that x actually can't be that value. All right, so let's go ahead and put these points on the curve. So when x equals -1, we get y equals -1/3. X equals 0, we get y equals -1/2. X equals 1, we get y equals -1, but again, that's going to be a hole in the graph. And so what's happening with this graph is it's going down like this, but then we have a hole in the graph. And if you were to plug in some additional points closer to 2, you would see that you get this asymptotic behavior. Now, on the right-hand side, when I plug in 3, we get 1. When I plug in 4, we get 1/2. When I plug in 5, we get 1/3. And so we're getting that same asymptotic behavior on this side. And, of course, this gets closer and closer to the horizontal asymptote. So, bottom line, when you have a common factor in the numerator and the denominator, you still want to take that factor into consideration because x can still not be equal to the number that makes that factor 0. However, rather than getting an asymptote at that value, which in this case is x equals 1, we just get a hole in the graph. And so it's as if the graph is going along, but then you have this point that you have to jump over and then continue your graph. So that's the difference when you have common factors. For our last example, we look at an application of a rational function. Suppose it costs $45 a day to rent a car with unlimited mileage. What is the expression for the average cost per mile per day? All right, so to answer this first part, we're going to let x be equal to the number of miles driven in a day. So the average cost per mile is going to be the cost divided by the number of miles. Well, we know the cost is $45 per day, and the number of miles driven, we just said, is x. And so the average cost, we'll call that C of x for cost, is 45 divided by x. Part B says make a table and a graph for this average cost function. So I will go ahead and just bring in a table. And so if you drive 0 miles, the average cost is undefined because 45 divided by 0 is undefined. If you drive a half a mile, the cost is $90, right? Because 45 divided by 1/2 is 90. If you drive 1 mile, 45 divided by 1 is 45. If you drive 5 miles, 45 divided by 5 is 9. And so what you can see here is that as you drive more and more miles, the average cost per mile decreases. So the idea behind renting a car where you have unlimited miles is that this would be a great deal if you're driving lots of miles. Let's bring in a graph. So in this graph here, we have the x-axis here is the number of miles, and the y-axis up here is the cost. Okay, and that's the average cost per mile. And you can see exactly what is being described here. So as you drive more and more miles, the average cost per mile comes down, right, substantially. And you can see that we have asymptotic behavior here. So because the degree of the numerator, this is a 0-degree polynomial, and the degree of the denominator is 1. Since the degree here is greater than the degree here, we know that y equals 0 is the horizontal asymptote. And so as you drive more and more miles, that average cost is approaching 0, right? So if you drive 1,000 miles in one day, the cost per mile is only going to be 4.5 cents, right? $0.045 is 0.45 cents. And so it's a really good deal if you're driving lots of miles. But if you don't drive that many miles, you see that your average cost per mile is actually really high. So it wouldn't make any sense to rent a car with unlimited mileage unless you were planning on driving lots of miles. And I think I've already answered the question for part C as well. All right, I know this was a long one. Get practicing now.